So yeah, unit one, linear relations. So we can either have a direct linear relation or a partial linear relation. And as a quick reminder as to what the heck those two things are, a direct one is a line that, first off, it's linear relations. It is all straight lines. So if I look at this one here, I know this is a direct linear relation because it's going through the origin, which is 0, 0. Right? It's going through the origin. This tells me it's direct. Think about how much money you make if you work at a job. If I work 0 hours, I'm making $0, right? Whereas if you have a partial linear relation, that's where it's not starting at 0, 0. And you can either have, remember, if you go from left to right, that's positive. If I'm going down, though, like this, negative. If you're looking at this top line here, this one that's going positive on this right side, well, maybe that's an example of, oh, this is a contractor who has a $200 call out fee. When I call the plumber to, maybe I have like water coming out of somewhere, I need him to come. Doesn't matter whether it's a 10-minute job or whether it's a 10-hour job. He's going to charge me $50. Come on out. So that could explain like this jump here. But so direct goes through 0, 0. A partial linear relation does not. But either way, it's going to be a straight line. Now, we have seen as well, what if I want to figure out how fast something's going up? We call that slope, which is also m, which is our rate of change. Or steepness. I know there's a lot there, right? But it all means the same thing. It's all interchangeable. So every straight line, every linear relation, we'll use more proper terminology. Every linear relation can be expressed in the form y equals mx plus b. Make that a little, ooh. I'm actually just gonna get rid of that and I'll repost it. Y equals mx plus b. I'm gonna make that a little bit bigger. Oops. So everything is expressed in y equals mx plus b. And what we know is, make that a little bit smaller. I'm going to move this over here, actually. Again, you don't have to, like, whatever works for you. But m is equal to our slope, right? Whatever that slope is, the steepness of it. And we also know that b is equal to the y-intercept. And so if you recall, your y-intercept is when it passes the y-axis. Yeah. So if I give you something like this, if I give you a line that's like this, for example, this would be my y-intercept. I would have a y-intercept. Let's say it's 5. You know, maybe I'm like, hey, that's 0 and 5. Well, if that's the case, then my y-intercept in this case would be 5. So you're looking at when it crosses that line. So it's literally called the y-intercept, when it intercepts through the y-axis. Now, the other thing is, what if I give you a line and I want, hey, I want you to find the slope of this. Well, you want to always be able to confirm it with 2 points.
Y squared minus y.
Yeah, so we have that second formula as well. This is technically like, so we know that m is equal to rise over run. This is technically that same thing. It's showing the rise over the run over time. But I'm going to use blue here. So if you need to find a slope, m is equal to the second y minus the first y divided by the second x minus the first x. And again, what do most people struggle with there? Identifying what is what. How do you do that? You pick 2 points. You pick 2 points and you label them, right? And you read a graph from left to right. So if I'm looking at my points here, well, this one I've done is my x1 and my y1, right? Because it's the first point I see. This is the first x, this is the first y. And the second point I've picked is my x2 and my y2, because it's the second points that I've picked. Right. So at this point, like we should now, so the goal here is you're able to find a you're able to find a equation for any line at this point, or you're able to draw any line from an equation, right, with a table of values. Now the one question here is, you know, what do you do if I have 3 of these things? I'll use red to kind of show that. You know, what if I tell you that, hey, I have a point that goes through let's say it's like, hey, I have a point that goes through 3 and 5. Well, this is an x and a y. And if I tell you, hey, it goes past the y-intercept at, you know, something, well, you have 3 things. You now have 3 things. You can find the slope with that as well. You have 3 things. You can find a 4th thing using that equation. So you use these 2 equations interchangeably, basically, just depending on what you need it to do. But just like anything, if you always have 3 things, you can always find whatever's missing. So this was 1.1 and 1.2, and there was also 1.3, which, if you recall, was lines of best fit. You know, if I give you a whole bunch of points that are like this, I'm just picking random points right now. So if I'm looking at this, oh, well, what's telling us with this data? Well, this is actually telling us that this data is, it's a, you know, this one in this case would have, you don't have to write that down, but it would have like a positive slope. It would be trending upwards. But some of the words we had here were the correlation. In this case, it's either a yes or a no. And there's also a strength of correlation. It can either be strong or it's weak. So let's think about it this way. If I tell you that, hey, this is a set of data, is this correlated to anything? You might be, well, yeah, that kind of looks like it is. Maybe this is someone's, maybe this is showing their height over age. Well, yeah, usually, you know, as someone's growing up, usually the older you are, the taller you are, right? There's a reason that 10-year-olds are usually bigger than 6-year-olds. So maybe this graph could represent that. So what I did here was I drew a line of best fit. So sometimes what you have to do is you have to see like, is this data correlated? Yeah, it kind of looks like it. It's age and height. That seems to make sense. Then you want to draw a line of best fit. And if you remember, that's just a line that seems to match the most. You want to try and have an equal number of points above and below. I actually didn't do a stellar job here, but maybe something like that. In this case, oh yeah, it looks like I have 5 points above. I have 6 points below. I have 1 point on it. That seems like an okay line of best fit. It's always going to be a little bit different, but you're just trying to find something that seems to have an equal number of points above and below. And not only that, maybe they look like they have an equal distance about it as well from that line. So you're trying to find lines of best fit. In this case, the strength here would be, it would be correlated, but these points are really far away from our line of best fit. It looks like it's a little bit of a weaker correlation, if that makes sense. So yeah, that's unit 1. So all in a nutshell is we looked at linear relations, direct and partial. We looked at how to find slopes using lines. We looked at how to find equations, how to find y-intercepts, how to find missing pieces of an equation. We looked at lines of best fits. This is called the scatter plot graph here. We looked at the correlation and the strengths of those correlations. So a lot of stuff, right? We spent a week doing that. You just got it in 10 minutes. So now we're going to move on to our next one of unit 2. Make that bigger. Which was limits to measurement. So one thing that's really important to note here is that with these limits to measurement, it primarily deals in stuff like, there's a couple of facts, measurement facts. With metric, the most common ones you're going to need to know are going to be millimeters, centimeters, meters, and kilometers. Now, if you remember that big chart we had where you times it by 10, you divide it by 10, you move the decimal for each thing you go up, there was stuff like decimeters, decameters, hectometers, stuff like that. These are the main 4 you're really going to need. And as you know, if you're moving to the right, if I'm converting a centimeter to a meter, well, what's happening? It's getting smaller, right? 100 centimeters is only 1 meter. So what are you doing? You are dividing by tens. In this case, we know there's 100 centimeters in a meter. It's not quite going to work out that way. There's a missing gap here that I'm just ignoring, because I don't think you need to have them memorized. I've yet to see that. Knowing if someone knows the difference between a decimeter and a decameter is just kind of a dick move. I don't think the government wants to do that. But the same thing goes true with, I go the opposite way, is it's going to increase. 1 kilometer is 1,000 meters. Oh, how many centimeters is that? That's 100,000. So it's being multiplied, or you're moving the decimal to the left. No, to the right. There was also a couple other facts. If we're looking at the imperial system, that sounds right. We know that 1 foot is equal to 12 inches. And I don't think you're going to have to memorize this. You might have to do the math with it, but they'll give that to you, I'm pretty sure. And 1 inch is equal to 2.54 centimeters. I do not think they're going to do that to you, but just kind of nice to know. So like if they're telling you, like if they're giving you like a thing of measurements, they at the very worst, they should tell you that 1 inch is equal to 2.54 centimeters, or like some other weird thing. They should give you that scale at least. So there's a couple definitions as well. We have accuracy. Now, if you remember, this is how close a measured value is. Where something like precision is used to identify the smallest unit of measurement on a device being used. If I am looking at the clock that I have here on the bottom right of my screen, it says 12:51 p.m. My precision is to every minute, right? I don't know how many seconds there are there. It doesn't tell me. My clock doesn't tell me. Your stove usually goes up by 5 degrees, right? So what's your precision of a stove? Usually 5 degrees. That's the precision of it. It can't go any better. Sorry, you can go to, well, that's a weird one. Which brings us into uncertainty, which is the margin of error in a measurement. Uncertainty. So what is uncertainty? Well, if I'm looking at the same clock here, again, I know that I can measure up to a minute, but I am uncertain to how many seconds that is. I can be 30 seconds ahead or behind. And then the formula, wait. Oh, right. The formula for uncertainty is half the precision. Okay, so like, what if I give you a thermostat? Well, thinking about those old Mercury ones with the red in them. I'm just going to fill that in really quick, just kind of figure. There we go. I have a thermostat there. Right. So what if I'm like, I don't know, maybe this is 20. This is 10. You know, this is 0. This is, I don't know, minus 10. I'm just picking random numbers here, right? In between, so right now, not a very accurate one, right? But eventually you kind of get stuff that kind of like splits in between. A lot of them, like, you know, kind of look like this. Again, I'm just drawing an undefined number of lines right now. The number of lines I'm drawing does not show something. It's just used to kind of prove something in a second. So if I want to know, like, hey, you know, what's the accuracy, the precision, stuff like that, or a tolerance as well. So like, let's say, for example, I'm like, hey, right now, this looks like the temperature is 16 degrees, right? If I'm looking at what I drew here, it looks like, you know, maybe 16. But what actually, if I'm looking at this, there's a range here. This is only so accurate. There's only so much of precision. There is an uncertainty here. So if my precision that I've said here is, hey, each one of these dots is 1 degrees, right? 20, 19, 18, 17, 16, 15. It's going up and down by 1. So if my formula for uncertainty is half of the precision, if my precision is equal to 1 degree Celsius, yeah, it would be, my uncertainty would be, you're right, 0.5 degrees Celsius. So what does that mean the temperature actually is? Well, the temperature could be 15.51 degrees all the way up to 7.4. Sorry, let's just make it easy. Let's do that to just prove the point. Sorry, it's supposed to be 16.5. So the temperature could actually be anywhere in between this in real life, but I'm limited by how accurate the tool I'm measuring with is. And so eventually, once we have these concepts, those are what form the foundation. You can then apply them, usually like manufacturing stuff. Usually we look at tolerance. The example I used here was a bag of chips, right? If I have, hey, I have a 50-gram bag of chips. But maybe the company allows 49 grams to 51 grams, right? It's, that's the difference of like a chip or two. It's not going to be exactly perfectly measured. They're like, we're okay if we give them a little bit extra. We're okay if we take away a chip accidentally. But on average, our bag should be 50. So so our tolerance in this case would be 2 grams. An official definition for it is it's measurement variation allowed. I've said, hey, with this bag of chips, if I'm the Lay's Potato Company, I'm okay with a 2-gram tolerance where, but you're like, well, but it only goes up and down by 1 gram. But in total, it's a 2-gram difference here, right? That's where I'm getting that number from. There's a couple things here. But so what's that 50 grams then? Well, the 50 grams is my goal. That's my target. Mathematically, the definition for that would be, we call it the nominal value. So the nominal value in this case would be 50 grams. And if you remember, there's 4 different ways of representing that, which you are not going to have to memorize. But there was, test my memory here. Oh yeah, there's the min value. I'm sorry. And the max value, yeah. So the minimum value would be, I'll just literally write it in. The minimum would be 49 grams. The maximum would be 51 grams. I'm just going to type it. So the min is 49 grams. The max is 51 grams. Right? That's one way of doing it. So there's 4 different ways. I'll split them up to better distinguish them in a second. One of the other ways is we take the nominal value plus or minus 1/2 of the tolerance. So plus or minus 1/2 of the tolerance. In this case, this would be 50 plus or minus 1 gram, right? Because our tolerance is 2 grams. I've just cut that in half. It's saying this can be either 1 gram higher or 1 gram lower, but I'm okay with that. So there's two methods. A third method that we do is it's the min value plus the tolerance minus 0. Oh my God. There. So it's the min value plus the tolerance or minus 0, which is basically saying that, hey, the chips need to be 49 grams. They have to be at least 49 grams. That is non-negotiable, but you can be up to 2 grams heavier. You can have up to extra 2 grams. Because remember, we said 51 grams is fine. But you can't make it any smaller. That plus is plus 2 grams. You can go up to 2 grams bigger, but you cannot make those any lighter. You cannot put any less potato chips in there. And then the other one here is this same thing, just reversed. What's the max volume that we're allowed to have? Oh, sorry. I wasn't asking. Sorry. I will in a second, but I'm saying, hey, you can have the max volume, but you can't add any more, but you can take away a little bit. So if you're applying to this potato one, you're right. The maximum volume is 51 grams. But I've said that you can't add any more, plus 0 grams. You cannot add more, but you can take away 2 grams. So those are the 4 different ways that you can represent something. Now, you do not need to memorize those. If they ask for it, they will give it to you. They'll ask it, give it to us in this form or this form. Like they'll ask you. Or they might be like, pick one that isn't right. So like, which one here is wrong? And they'll give you something like that. And that's unit 2. Sorry, I'll go back to that. So and that's unit 2. So like that's it. So in 30 minutes, you got 2 weeks worth of stuff kind of pushed onto you. So what's going to happen now? My recommendation is I'll make that bigger. Look at your unit 1 and 2 workbooks. I have the blanks uploaded on the LMS. If you want to I'm not going to print them out, obviously. You can look at the new ones or the old. So you can look at the ones you've done or new ones. Go to the chapter test at the back. See if you're able to do that. Those are some really good exercises to be able to do. And if you're stuck on something, ask. Like this is if you walk out of here, you're like, I don't know how to do tolerance. You're not going to have that epiphany in the middle of the exam. At best, you're going to get to guess. So if you don't know something, now's the time to ask. This was not meant to be a full reteaching. This was meant to be a refresher of stuff. You will gain a lot of value by going back and looking at your notes. Specifically, maybe like some of the examples or definitions that we did. That's not to say like I don't want to help you. I do. I'm just saying you might find some information there. If you're just like, I don't know what tolerance is, spend 2 minutes, look at tolerance, and then if you apply it to a question you still don't know, happy to help out. So yeah, with that, we got 2 hours to work on those 2 units there.